When an electron moves in a straight line, it creates a magnetic field in the shape of a circle in its wake. If instead of moving in a straight line, you cause the electrons to move in a circular fashion, they create what looks very much like a bar magnet. If you flip the polarity of the battery, you also flip the polarity of the magnet it creates.
Alright guys, we're about ready to wind our first electromagnet. We're going to be using this armature here, which is a little tube. This one's made out of plastic. However, most of the time you're going to find that they're made out of ferrous metals, although we'll explain that later. So basically a tube, and then we need some sort of wire. Right now we're going to be using annealed copper wire. Copper wire has really low resistance, so it's great for this application. And the annealing makes sure that we don't have any electricity jump between the coils. So it just keeps it non-conductive on the outside. That does, however, mean we're going to have to rub that off at the end, and I'm going to show you the process for that too. All right, let's get winding. So basically, you're going to want to start this off. It's as simple as it sounds. You're just going to want to wrap it in a loop. So you see the loop I have here. So now it's nice and tied tight. And now we're just going to start wrapping. So hold one end like this. You just wrap it like this. Now you'll end up doing this until you get a few hundred turns. This is for a relatively simple electromagnet. You can end up with a much more complicated geometry if you're looking for different shapes in your field, but for just a regular bar magnet style, this is what you're going to be doing. We could have wrapped a lot more. This is not the one we're going to be using. This is just my example. Have a much thicker wound one over here. We also put a little bit of glue on top so that everything stays nice. So this is the end product. This is a few hundred turns. I think we've maybe got to 30 with this one. But let me show you next how we're going to remove the annealing, and then we'll be ready to use it. The annealing is what gives it that nice shiny color. And we're going to remove that so that it becomes conductive just on the very ends. We're just going to remove the annealing by rubbing the Dremel tool against the outside here. And now the end is not shiny at all. In principle, we do this to the other end as well. However, I've already made up a few coils. All right, guys, so we're going to be actually using our electromagnet. I have a power supply here. It's set to 3.25 volts. So 3.25 volts is going to give us about 1.7 amps, which is perfectly acceptable. We don't want to go too high because of how small this is. It won't dissipate heat very easily. And it has a plastic core, so that would melt pretty quickly as well. Basically, you attach the red wire, which is your positive, to one end, and then you attach your negative wire to the other end. Now, when we put it in here initially, you might see a little bit of jiggling, but it doesn't do much. We need to include a ferrous core. So any sort of iron core, otherwise known as a ferrous core, is going to amplify the effects of the magnetic field. Now when we go in there, we can pick up a crap ton of these. So you can see obviously it's a little bit different when we have our iron core.
This example circuit shows us how polarity flipping works. By flipping the ends of the battery, we cause the current to move in the opposite direction. And because the diodes only allow current to flow in one direction, we turn on and off the LEDs in this fashion. By placing a device called an H-bridge in between, we can effectively switch the polarity of the battery without any mechanical movement, with a simple press of a button or the switching of a pin from high to low on a microcontroller. Let's swap out this circuit for a coil once again. This is the effective working principle for most electromagnetic devices, including motors and actuators. This rapid flipping causes a rapid changing in force and even creates electromagnetic waves.
All right, so let's take a look at our next circuit. The main star is going to be this H bridge here. This is going to allow us to flip the polarity of the coil without actually changing the position of the electrodes. So we'll be able to flip with just a button. There's outputs on this side and inputs on this side. Voltage and ground go here, and then we can plug our coil in or any circuit we want on this side. The control pin here controls what direction current flows. When this is low, current will flow one direction, and when this is high, it will suddenly switch and start flowing the opposite direction. So basically, this pin here controls if current goes from the top pin to the bottom pin, or from the bottom pin to the top pin out here. We're going to plug our coil in right to those two pins, and we're going to use it to switch back and forth the polarity of the magnet we create. Alright guys, we're ready for a really cool experiment now. Basically, we're going to use this H bridge to flip the polarity of the electromagnet here. Now, there's a permanent magnet inside, so when their polarities agree, it's going to sit in there just fine. However, the moment we flip, it's suddenly going to find itself wanting to escape, and we're going to see it shoot out. We can also get a couple other cool effects, so it wants to be in here. And now let's just play around with this button and see what happens. Oh, we're moving it a little. Alright, so I'm just going to use the button here to change this H bridge from high to low, which is going to switch the polarity for us. 3, 2, 1. So, as you can see, it launched those magnets out. And actually, not only that, they're a little bit hot. I can feel the magnetic field is applying energy to these magnets. So that's pretty cool. And let's put it back in, see if we can get some more cool stuff to happen. So if I'm playing around with the button, I can get to change quick enough that the magnet doesn't have time to leave. So I can get to dance a little bit. Let's see if we can get to dance. Oh, maybe not. There we go, we got it a little. Whew.
So how powerful is our magnet? The strength of the magnet will depend on the amount of energy that actually reaches the coils. No driver is 100% efficient, and so at least some energy is wasted by the driver as heat. Plugging different drivers into the same 6 ohm coil and running at the same 7.5 volts yields dramatically different results. However, this picture gets dramatically worse when you realize you have to raise the total voltage in order to get the same power to the coil.
So anytime you use a driver, you're going to lose a little bit of energy. That just depends on your efficiency rating. For some of the older drivers, you can get down to 75% efficiency. For some of the newer stuff, you can get up to 90% efficiency. This A.R.A.M DHB is around 96% efficient at this voltage, which is really good. That means that only around 4% of the energy will be wasted as heat on this board, and 96% will go to the coil. That does not mean that 96% of the heat will go right to the magnetic field. Much of this will come off as heat too, but that depends on how exactly you wound the coil and the properties of the electromagnet. All that is saying is that only 4% is wasted here. So we're going to do a heat test, And we're actually gonna see how hot this board gets while this one heats up. So I'm actually just gonna hold this in my hand. We're gonna start off at 3.25 volts like we did before, and then we're gonna up it and see what happens. So we're at 3.25 volts now. Let's up it to 4 volts, 5 volts. We're running at about 2.3 amps. This board is rated for about 2.5 continuous, so this will be fine to do continuously. Now we get up to 6. We're at about the limit of what this board should be doing. And let's get up to 10 volts. Nice, so this is 10.25 volts. We're running about 3.2 amps through it. As this heats up, the resistance of these wires actually increase. All right, let's see what smokes first. So I'm still holding the driver just fine. All this stuff. Let's see. It's likely gonna be, oh, here we go. Yep, so you can see now the plastic is melting. All right, guys, I had to unplug that because this coil was physically smoking. That's crazy. So the coil got so hot, and I'm still holding this just fine in my hand, but the coil got so hot that this plastic is melted. Watch this. I can physically squeeze the plastic just together. There we go. Look at that. Actually, the plastic is so melted I can move it with my hand. That's crazy. Yep, and the board still can hold it. So that's what you're looking for, is a high efficiency driver like this one.
Now that we know how much energy actually goes to the coil, how do we maximize the field? We could squeeze the coils closer together, but this has the drawback of making the total field smaller. So instead, many times, you'll simply opt for a thicker wire with lower resistance.
Alright guys, so that's pretty much everything you need to know to drive your first motor. We didn't explicitly get into motors here, however, motors are pretty much just magnets. So get in there, try your first motor. If you want more information, I'll be releasing a video later on that goes further into motors in particular, one specifically on DC motors and one on stepper motors. There's also a lot of other great content on YouTube right now you can go watch, or just go try it out yourself. Nothing is as scary as it seems, just go try it out. It's gonna be a lot of fun. So using these same techniques, you can drive a stepper motor just like this one. Basically, all you're doing is switching magnets back and forth. If you guys found that video informative or entertaining, please drop a like and subscribe, or share with your friends. Also, if you want to, please go to our website to pick up one of our H bridges, or our dual H bridges, which is driving the stepper motor here, and support us as well. And you can get 10% off of our Tindy storefront using this discount code. Thank you guys all for watching, and have a great day.